All right, welcome back. We're going to shift gears a little bit here. We're done talking about sort of the basics of probability, and what that means is that we can start to build up probability models, and we're going to use the basics to kind of do that. Before we get to specific kinds of probability models or probability distributions, we need to just kind of introduce the concept generally. And so that's what the topic of discussion is in section 2.5. So we're going to talk about random variables, and we're going to talk about probability distributions. So just to get us thinking about this, a random variable is a variable. It's usually going to be represented with a capital X, and it's a variable that has a single numerical value determined by chance for each outcome of a procedure. So, for example, the outcomes of flipping a coin 2 times, okay, so for flipping the coin twice, we could get heads both times, or we could get heads and then tails, or we could get tails and then heads, or we could get tails both times. So those are all of the possible outcomes. We make a random variable out of this by doing something like counting up the number of times that heads occurs, right? So if x is the number of times that heads occurs, then x is a random variable. Note that x cannot be less than 0, okay? It doesn't make sense to say, oh, we flipped -3 heads when we flipped the coin twice, right? So we say probability x is less than 0 is 0. That cannot happen. But x could be equal to 0, right? It's possible that we might never flip heads when we flip the coin twice. In fact, of our 4 possibilities, there was one where heads never occurred. So the probability that x equals 0 is 1/4. As for the probability that x equals 1, well, if x equals 1, that means that we flipped heads exactly once. And there were 2 possibilities, 2 ways that could happen out of 4 different options. So probability x equals 1 is 2/4. Or you could reduce it to 1/2. And then finally, the probability that x equals 2, well, this would mean that we flipped heads both times, right? And there was one way that could happen, okay, out of 4 possibilities. So probability x equals 2 is 1/4. And then finally, the probability x is greater than 2. Well, it's not possible for x to be more than 2. Remember, x is the number of times that we flip heads in 2 coin flips. It's not possible that you're gonna flip heads more than twice if you're only flipping the coin twice, right? So probability x is greater than 2 is 0. So the possible values for x are 0, 1, and 2. And those are the only possible values that x can be, okay? A probability distribution is a function that describes all the possible values and likelihoods that a random variable can take on. So what we have right here is basically a probability distribution, okay? Probability distributions can be given either as a table or as a formula. And these rules are called probability density functions, or PDFs for short. So for example, if x is the number of times that heads occurs in 2 coin flips as above, then the probability distribution for x would be, we would list off the possible values for x here, together with their corresponding probabilities here, right, on the other side. So probability x is 0, we said was 1/4. Probability x is 1, we said was 1/2. And the probability x is 2, we said was 1/4. And that's our probability distribution. Now, random variables are numerical, right? So x is going to be a single numerical value. And like any numerical variable, a random variable can be discrete, where we obtain the values by counting, or it could be continuous, where we obtain the values by measuring, right? So for the coin flip example, x was discrete. We counted the number of heads. Discrete distributions are usually given as tables, not always. Okay, and continuous distributions are usually given as PDFs, but not always. From the coin flip example, we can see that when the probability distribution is given as a table, okay, it looks a lot like a relative frequency distribution. In fact, when these probabilities are obtained empirically, then a probability distribution is exactly the same thing as a relative frequency distribution. They're just exactly the same thing. Okay? The reason I point that out is just because to emphasize that this really isn't new. We're going to take a lot of things that we already know and reframe them in this section in terms of random variables. But none of it is really completely new. Let's look at an example, a few examples where we work with some probability tables or probability distributions, right? PDFs. Okay, this first one says, in the following table, the random variable x is represented or represents the number of marriages an individual aged 15 years old or 15 years or older has been involved in. So x is the number of marriages someone aged 15 or older has been involved in. Let's hope that most of these zeros are like 15 to 18 years old. Let's hope there aren't a lot of 15-year-olds getting married. Anyway, part A. What's the probability that an individual was involved in 2 marriages? So we want the probability x equals 2, right? We could write that as probability x equals 2, or we could simply write it as probability of 2, right? Probability x equals 2. And this is just asking us if we can read the chart, right? And, well, there's the probability. It's 0.121. So there's like a 12% chance, okay, that an individual has been involved in 2 marriages. Part B, what's the probability an individual was involved in at least 1 marriage? At least 1. Well, at least 1 would mean 1 or more, okay? So that would include all 3 of these possibilities, right? If you've been involved in 2 marriages, then you've been involved in at least 1 marriage, right? Or if you've been involved in 1 marriage, then you've been involved in at least 1. Okay, so this could be encoded as the probability that x is greater than or equal to 1. And using our probability table, we would just say, well, this is the probability x is 1, plus the probability x is 2, plus the probability x is 3. Okay, so that's 0.575 plus 0.121 plus 0.032. And if you punch that into your calculator, it comes out to 0.728. Okay, so this is how we work with probability models, okay? Let's look at another one. Here, we're not given a chart, we're given a PDF, right? We're given an actual probability density function. And this function is supposed to represent x here is the number of heads flipped when a fair coin is flipped 4 times. Since we're flipping the coin 4 times, it's possible that x, right, the number of heads, could be anything between 0 if you never flip heads, or 4 if you flip heads every time. It's not very likely that that will happen, but it could happen, right? So part A asks, what is the probability that heads is flipped exactly once? So we want probability that x equals 1. And we're going to use the formula that we were given here to compute that probability, right? We'll say it's 0.0625 times 4 choose x, but x is 1 in this case, right? So use a calculator that has combinations on it. I've used the Desmos calculator to show you how to do this before. And if you punch this into the Desmos calculator, you get 0.25. So there's a 25% chance that heads is going to be flipped exactly once. Part B, what's the probability that heads is flipped at most once? Okay, at most once. If it's flipped at most once, then that means it wasn't flipped twice or 3 times, right? It must have been flipped 1 time or 0 times, okay? So probability that x is at most 1 would mean x is less than or equal to 1, okay? And that's going to be the probability that x is 0 plus the probability that x is 1. So that's 0.0625 times 4 choose 0 plus 0.0625 times 4 choose 1. This one, right, 0.0625 times 4 choose 0, if you punch that into your calculator, you should get 0.0625. And this one we just did above, right? It's 0.25. And then if you add those together, you should get 0.3125. And that's how that works. Okay, one more example like this. It says, you roll a fair six-sided die. Let x be the number that you roll. Find the probability distribution of x. Give both a probability density function and a table. Okay, so we want both a function and a table. Okay, so our table would look like this. X is the number that we roll. Let me try to write that a little more neatly. X is the number that we roll on the die. Well, it's a six-sided die, so there are 6 possibilities. We could roll a 1, a 2, a 3, 4, 5, or 6. The probability that we roll a 1 is, well, it's 1/6, right? There are 6 numbers on the die, and only one of them is a 1, so the probability of rolling a 1 is 1/6. The probability of rolling a 2 is not 2/6, it's also 1/6 because there's only 1 2 on the die. And the probability of rolling a 3 is 1/6, and so forth, right? These probabilities are all the same. So it's kind of a boring one, but that's how that probability distribution would look. To give a PDF of this, we might say something like probability of x is equal to 1/6, right? It doesn't matter what x is. Well, actually it does. Let me amend that a little bit. Probability of x equals 1/6, assuming that x is between between 1 and 6. Okay, so this is what the true probability density function would be. Okay, so that's that one. Of course, you can give a graph of a probability distribution. For a discrete random variable, the graph of our PDF is going to basically just look like a histogram, okay? Whereas for a continuous random variable, the graph is going to look like a smooth curve, like this, okay? And the reason for the difference is that if you have a discrete variable, then, you know, x can be 0, but it can't be like 0.5, right? And x can be 1, but it can't be 1.7, right? Like it's discrete, and so there are gaps between the values that x can take on. And so, you know, the probability that x equals 0 or the probability that x equals 0.13 are the same, right? They're all represented by this bar that extends from 0 to 1, right? And the probability x is 1 is this bar, right? This would include all of the possibilities for x that are between 1 and 2, not including the 2. And so anyway, so you just get these flat kind of probabilities and that ends up creating a histogram. Excuse me. For a continuous variable, though, x can take on any value, right? It's continuous, it's measured, and so it could be anything, right? X could be 1, but it also could be 1.3 or something, okay? And so so we represent the likelihood that x takes on a particular value with a smooth curve in the case of a continuous variable. This is not something that you're going to have to worry about a ton. I'm just pointing this out because we're gonna often see continuous distributions represented with smooth curves, like the normal distribution. We've already looked at a bell-shaped distribution, and when we looked at the empirical rule, we just gave kind of like a smooth curve version of it. And this is why. Because oftentimes when we're dealing with a bell-shaped distribution, we're dealing with some kind of continuous variable. So anyway, we'll see these kinds of things often. For now, let's just remind ourselves how to draw a histogram, right? It says, number 4 here, draw a graph of the probability distribution below. X represents the number of rings on a person's left hand. Okay, some people don't have any rings on their left hand. Some people are married and they have one ring on their left hand or whatever. So here's what it would look like. Let me try to do better. Okay, so along the x-axis, we need to put x, right? So 0, 1, 2, 3, etc. 1, 2, 3, 4, 5. Let me give myself a little more space so that I have room to draw those bars. And then along the y-axis, I need to put the probabilities. The largest probability looks like 0.38. So I need my y-axis to go up to, let's go up to, let's say 0.4, and we'll just go in increments of 10. So 10, 20, 30, 40. So this may not be the best graph ever produced. That's okay. And then we'll draw our bars, right? So, by the way, 0 is right here. So the probability x equals 0 is 0.18. That would be right about that. Okay, so there's that first bar. Probability x is 1 is 0.38, so that's going to go right about there. Probability x is 2 is 0.23. Oh, I'm drawing it too low. 0.23, right about there. 0.10, 0.03, and 0.08. So you get a graph that looks something like this. We've done these kinds of graphs already, but I'm just showing you that, hey, you can do this with probabilities just like you could with frequencies or relative frequencies. This is number of rings down here on left hand. You could give this thing a title, but anyway, that's the idea. Let's talk about the mean and the standard deviation of a random variable, okay? For reasons that will become clear later on, when we're analyzing a probability distribution, we like to make special note of its shape, its center, and its spread, which should sound familiar, right? These are things that we're interested in when we're describing a data set, when we're giving a data profile. With a random variable, we look at the shape by looking at a graph of the distribution as described on the previous page. As for the center of the distribution, right, we're going to use the mean, mu sub x, to measure the center of the distribution. This is regardless of the shape of the distribution. So even if it's a skewed distribution, excuse me, even if it's skewed, we'll still use the mean. And again, the reasons for this will become clear as we develop more information and get through the material in this unit. Now, we can't compute the mean by adding up all the values and then dividing by the number of values, because we don't have raw data to go off of here. All we have are things like this, some kind of theoretical distribution. So we have to do something else, and what we'll do is we'll basically use that formula that we learned about in section 1.7 when we were talking about how to compute the mean from grouped data. Okay, this is that same formula in disguise. It's the same formula, but it's just expressed in terms of random variables. Okay, what we're going to do to compute the mean is we're going to take each value that x can take on and multiply it by its corresponding probability, and then we'll add all of those things up. Okay, so that's how we're going to compute the mean for a discrete variable. For a continuous variable, that's a little more complicated. We would need calculus to do it. For those of you who have had calculus, right, this is how you would compute the mean of a continuous random variable, right? You would do an integral. We're not going to use that formula in this class, obviously. Okay. As for the spread, we'll use the standard deviation to measure the spread. Okay. For a discrete variable, this is the formula that we would use. Okay. So we're going to do the same process as we did here, only we're going to square the x's first. Okay. So we're going to square the x's, multiply by their corresponding probabilities, add them up. And once we've done that, then we still have to subtract off the mean. So computing the mean is going to be the first step in computing the standard deviation of these things. For a continuous variable, for those of you who are dying to know, you would also do an integral, right? This is the integral that you would have to do for that. Okay, let's look at a couple examples computing the mean. So number 5 here says, compute the mean and standard deviation of the following discrete probability distribution. In this case, x represents the number of windows in a one-bedroom apartment. Okay, so for the mean, right, we would say mu sub x equals the sum, and that's my attempt to draw the Greek letter sigma, right? It's a sum of x times p of x. Okay, so in this case, that's going to be 2 times 0.15 plus 3 times 0.2 plus 4 times 0.65. And then you punch that into your calculator just exactly as it looks. Well, assuming that you're using a nice scientific calculator like the Desmos calculator. And then you get your answer. So let me punch it into mine real quick. 2 times 0.15 plus 3 times 0.2 plus 4 times 0.65 comes out to 3.5. So on average, one-bedroom apartments are going to have 3.5 windows. Or maybe to make it make more sense, you could round to the nearest whole number and say, well, on average, we expect them to have 4 windows in them, right? Okay, we still need to do the standard deviation. So to do the standard deviation, the first thing I'm going to do is I've already got the mean, right, which is good because I need that for my standard deviation. So then let's compute this chunk, right, where we want to take x squareds and multiply by their corresponding probabilities. So just to compute that part, right, this is going to look like 2 squared times 0.15, right? 2 squared times 0.15 plus 3 squared times 0.2 plus 4 squared times 0.65. And let's see what I get when I punch that into my calculator. So this is going to be 4 times 0.15 plus 9 times 0.2 plus 16 times 0.65. That comes out to 12.8. So now to get the standard deviation, sigma, the standard deviation of our random variable x, right, sigma sub x, is the square root of the sum of x squared times p of x minus mu sub x. Oh, and by the way, I've got a typo. This should be mu sub x squared, right? We've got to square that value. I'll fix that in the notes before I post them on Canvas, so you should have that correction in your notes. It should be squared here as well. Okay, so in our case, this is going to be the square root of this chunk of the formula is what we just computed above, right? It's the 12.8. This chunk of the formula is what we computed when we computed the mean, right? Only we have to square the value. So maybe let me be more careful, right? This chunk is that. So this is going to be minus 3.5 squared. Okay, but we can punch this into our calculator now and see what we get. We're going to almost certainly have to round. So let's see. We've got the square root of 12.8 minus 3.5 squared. Whoops, 3.5 caret 2. Okay, so that comes out to about 0.74 if we go to 2 decimal places. We could go 0.742 if we go out to 3 decimal places. I'm happy with 0.74 as my answer. So that's how that would work, right? So we've got our mean and our standard deviation. Next one asks us to do the same thing, I think. This time, instead of giving us a table, we're being given a probability distribution, okay, a function to work with. But we can still do this. I think in order to do this, probably the easiest thing to do is to write out the table first, because once you have the table like this, it's a piece of cake. So let's make the table. This function is supposed to represent the number of heads, x, obtained after 3 flips. Okay, so we've got x and we've got p of x. If x is between 0 and 3, if we're flipping the coin 3 times, right, it makes sense that the smallest x could be a 0, right? That's if you flip 0 heads. And the largest x could be is 3. That's if you flip heads all 3 in all 3 flips, right? So x could be 0, 1, 2, or 3. To get the corresponding probabilities, we're just going to take turns plugging in. First, we'll plug in 0 for x, right? And then once we've got that answer, then we'll plug in 1 for x. And when we've got that, we'll plug in 2 for x, and so forth, right? So let me just pause for a second. So I'm going to skip ahead and calculate these probabilities. You should maybe pause the video and see if you can get these probabilities on your own. Make sure you can get them on your own. Okay, so this is what you should have by the time you finish calculating those probabilities. So now we're going to compute the mean and the standard deviation of this table, just like we did for the previous one. So the mean, mu sub x, is going to be the sum of x times p of x. Okay, so in this case, that looks like 0 times 0.125 plus 1 times 0.375 plus 2 times 0.375 plus 3 times 0.125. And then you punch that into your calculator, which comes out to 1.5. So there's our mean. That makes sense, right? If you flip the coin 3 times, doesn't it make sense that on average you would expect to flip the coin or flip heads 1.5 times, you know, if you repeated the experiment over and over? Okay, standard deviation. Sigma sub x is the square root. Oh, actually, I'm going to run out of room if I try to write out everything. Let's just calculate. let's just calculate the sum of x squared times p of x. That's going to be 0 squared plus 0.125 plus 1 squared times 0.375 plus 2 squared times 0.375 plus 3 squared times 0.125. And you punch that into your calculator, and that comes out to 3. But we're not done yet, because now we can compute the standard deviation. Right, sigma sub x is the square root of this thing that we just computed minus the mean that we computed earlier squared. So that's going to be the square root of 3 minus 1.5 squared. So you punch that into your calculator, and that comes out to approximately 0.87 if we round to 2 decimal places. Okay, so this is how we compute the mean and the standard deviation of a random variable. Those are going to be very important for us as we go to try to compute probabilities, particular probabilities involving random variables, specific kinds of random variables. One last topic before we close out this section is that we can think of the mean in a slightly different way here. We can think of the mean as the expected value, right? The expected value is the value you expect x to be, okay? Going back to our coin flip example, if x is the number of heads that you obtain after 3 flips, well, 3 is kind of a bad example because it's an odd number, but let's say if you flipped the coin 4 times, right, you would expect to get heads twice, right, because there's a 50-50 chance of flipping heads. So if you flip the coin 4 times, you expect to flip heads twice, right? And that's what the expected value is. And the expected value is just, it's equal to the mean, all right? It's the same thing as the mean. So here I'm giving a different coin flip example, but okay, so to give a different coin flip example, if x is the number of heads in an experiment where a coin is flipped twice instead of 4 times, right, then the expected value of x would be 1. We expect out of the 2 coin flips to flip heads once. Now, if we use the formula, first of all, let's give ourselves a little table to go off of. So recalling the first page of our notes, right, x could be 0, 1, or 2. The probability x was 0 was 1/4. The probability x was 1 was 1/2. And the probability x was 2 was 1/4. Okay, so using our formula now, the expected value, which is the same thing as the mean, okay, is 0 times 1/4 plus 1 times 1/2 plus 2 times 1/4. And that would come out to 0 plus 1/2 plus 2/4. 2/4 is the same as 1/2, right? So this is just 1/2 plus 1/2, which equals 1. Okay? So it kind of validates our intuition, right? That the expected value is the value we expect x to be, and it's the same thing as the mean, right? This is the way that you would compute it. Now, there are going to be less obvious examples here, right? And that's why the formula is useful. You might, in other words, I don't want you to get into to have the wrong idea and think, oh, I can always just use my intuition to figure out what the expected value is. That's not so. You need to use the formula, okay, to find the expected value. But another thing to say about this is that when we interpret the mean as the expected value, we will typically round to the nearest value that makes sense. For example, if x is the number of pets people own, and we have some probability distribution and we compute the mean, right? We might get something like this, right? Mu equals 3.7421. But you wouldn't say, well, if you go to a random person's house, you wouldn't say, I expect to find 3.7 pets there. That doesn't make sense, right? Because you can't have 0.7 pets. What you would do is just round to the nearest whole number and say, well, I expect to find 4 pets there, okay? Now, on the other hand, if we were talking about money in your bank account, right? And again, we got, something like the mean is 3.7421. Well, here, it doesn't make sense to talk about these digits because our money has to be rounded to the nearest penny, right? But you also wouldn't say that you expect $4 to be there, because what you would really expect is for $3.74 to be there. I hope you have more money than that in your bank account, but then again, I remember what it was like to be a student. So, so some of you probably would consider yourselves lucky to have $3.74 in your bank account. Anyway, let me just give you one last example here to illustrate kind of interpreting the mean as an expected value. Number 7 says, a slot machine requires $1 to play. The potential winnings at this slot machine are given in the probability distribution below. What amount of money would a player expect to win at this slot machine? What would the player expect the net earnings to be after 1 game, after 100 games, after 1,000 games? Okay. Well, to compute, so notice that question. What amount of money would a player expect to win, right? So we're going to be computing an expected value, right? The expected value of x. We want to know what value we expect x to be. Okay. So we're going to use our formula, right? This is the sum of x times p of x. That's going to be 0 times 0.75 plus 1 times 0.125 plus 2 times 0.0625 plus 10 times 0.0625. Okay, and go ahead and pause the video, pop that into your calculator. Let's see what we get. Okay, so I believe that comes out to 0.875. Okay, so that's the expected value, or the mean, right? On average, that's how much you would expect to win in a game. However, you might look at that, you might say, oh, that's a good slot machine then. I'm going to win 87 cents or 88 cents. That's not exactly the right way to interpret this, because you don't ever make 87 cents. You either make $0 or you make $1, or maybe if you're lucky, $2 or $10, but you never make 87 cents on a single game, right? It's just on average. If you play this game over and over and over again, this is how much you expect to earn on average. But you have to remember that you had to pay $1 to play, so you really lost money, right? You expect to lose money every time you play this game. Speaking of which, the next question asks, what would the player expect the net earnings to be after 1 game? Well, after 1 game, the expected winnings, so let's see. So after 1 game, the expected winnings well, if we round this to the nearest whole number, the expected winnings are $1. Or maybe it would make more sense to, well, no, because if you're only playing 1 game, you're not going to win 88 cents. So we'd expect $1, right? Expected winnings, $1. Okay? But the expected net, you have to keep in mind that you paid $1 to play, right? So you expect to win $1, but you also paid $1 to play, and so that's $0. So you expect to make nothing. Or rather, you expect to net nothing. Okay, so that's after one game. What about after 100 games? So after 100 games, well, now your expected winnings are going to be 100 times as much, right? Okay, it's going to be the 88 cents, right? 87.5 cents times 100, right? 0.875 times 100. So that would come out to 87.5. So your expected winnings are $87.50. But that's not how much you net, because you had to pay $1 every time you played. Okay, and if you're playing 100 games, that means you paid $100, right? So your expected net would be the $87.50 that you won minus the $100 that you paid to play, which would come out to negative $12.50. Oh shoot, negative $12.50. This is how much you expect to net after 100 games. So you're losing money. After 1,000 games, it's going to be a similar story, right? Your expected winnings are going to be that 0.875 times 1,000, which comes out to $875. Hey, that's exciting, right? You expect to win $875. Wow, that's amazing. Except that you had to pay $1 each time you played, right? So your expected net is going to be the 875 that you won minus the $1,000 it took to play 1,000 games, right? And so that's going to come out to negative $125. So you lose $125 after 1,000 games. Now, you may not mind that, I guess. If you like playing the slot machines, you might think it's worth it to pay that amount of money to sit there and play the slots. Personally, I don't understand how people derive pleasure out of that. Because there's no skill involved. You're just mindlessly like pulling a lever. But I guess there's a little bit of a rush. I think it's dangerous, you guys. So if you want my moral pontificating, I would say steer clear. I don't think it's a good idea. But anyway, that'll do it for this section. In the next few sections, we'll talk about some specific kinds of random variables, some specific distributions that will be very useful to us as we move through the remainder of the course. But until then, have a great day, and I'll check in with you in the next section.